Okay, so this is the start of chapter 2. We're only going to be doing the first part of this. Essentially, chapter 2 is looking at a type of molecule known as a polymer. Okay, so we're going to look at two types of polymers, addition polymers and condensation polymers. So we're going to focus today on addition polymers. So polymerization is the process of making a polymer. Okay, so it's important to know what we're looking at here. So this picture is actually a nice way to explain what a polymer is versus a monomer. So polymers are essentially long chains of repeating patterns or repeating units. The monomer is the molecule that we're going to use as that repeating pattern. So you can see here, right? So we have a monomer here, and then our polymer is the monomer that has been on repeat, right? Now polymers can be hundreds and hundreds and hundreds of molecules in length, right? So all the monomers all linked together. So essentially you have these like long chains. So a monomer is really the building block to create your polymer. Properties of the polymer are going to be very, very different. Properties are dependent on the original monomer. So if the monomer might have an OH group, so the polymer, of course, is going to have hydrogen bonding and dipole-dipole and all that good stuff, right? Or your polymer might have just hydrocarbons. Maybe there's a methyl branch, or an isopropyl branch, but they're all hydrocarbons. You can have benzenes on there. So really, you can have any molecule that you create your polymer with will have, of course, an influence on the polymer's final intermolecular forces. Okay, now how do these monomers link up to each other to make this polymer? So there's only 3 types of bonding links. So a carbon can link with a carbon. So you have a carbon-carbon link. You can have a carbon-oxygen link, or you can have a carbon-nitrogen link. Okay, so the one we're going to focus on today, addition polymers, are all carbon-carbon links. These 2 types of linkages are known as condensation polymers, and we will look at those in the next lesson. All right, let me just fix this here a bit. Okay, so addition polymers are the result of, you guessed it, an addition reaction. So the process of an addition reaction is what's going to be actually happening. Of course, it's a little bit different because our reactants are going to be multiple monomers. But of course, we need to start, just like any other addition reaction, we need to have an unsaturated bond to start with. So that means we need a double bond or a triple bond, but I'll be honest, addition polymers are pretty much all double bonds. Okay, so we're going to look at our first example here. It's kind of nice to learn this through looking at the reaction examples because it'll make more sense, I'm hoping anyway. Okay, so first of all, the naming system of this we'll get to. It's actually relatively straightforward. But anyways, ignore the name for now. What I want you to recognize is, let's go right to this reaction. The monomer we are using here is ethene. So this is actually the smallest type of monomer you can possibly have, because remember, we need a carbon-carbon double bond to make these polymers. So obviously the smallest amount you can possibly have is only 2 carbons in length. So notice they're showing us 3 ethenes here, but remember that these can have hundreds and hundreds of molecules in length. So you can have, 10,000 ethenes or 10 moles worth of ethene. But we're just kind of looking at what's the action, what's going on. So just like any other addition reaction, what happens is the double bonds break, and the carbons that are involved in that original double bond are now requiring a bond. So they essentially will bond with the next door carbon. So of course this is not being shown, but it attaches to another ethene, right? So eventually you get all of them. Notice now there are single bonds, no longer double bonds. So we can represent it this way. So what this is called, what this is showing you is, this is looking at an ethene polymerization with 3 repeating units. So what that means is they're showing you this reaction with 3 reactants written down. So notice here, this is like the original 3 reactants. Okay, so it doesn't mean that this polymer only has 3 molecules worth. It's just that's what we happen to be representing it with. Or, and this is a very common condensed version of showing a polymer, what they will show is 1 unit, what it looks like after the addition has happened. And notice these dashed lines are on the outside of this bracket. This means that on this side and on this side, there are additional monomers. Like a monomer would be here and a monomer would be here. The focus is on the middle to say, well, what happened to the original monomer? We now have a single bond. The N is really just representing, any number of bonds. So for us, if we're doing 3 repeating units, right, we're showing 3. But this could be many monomers, okay? I'm not going to ask you to ever show more than 3 repeating units, okay? That's more than enough for me to see that you are understanding what the reaction process is here, okay? So, of course, so when we're looking at this, the different types of compounds, let's look at the names. So we have, so the name that's in brackets, and actually this name that's here, polyethylene, is a common name. Okay, so it's not the IUPAC name. The IUPAC name, if you even want to ignore it, that's fine. I will always provide you the IUPAC name. So actually, take a look. It's polyethylene. So what it is you have the monomer name, whatever the monomer was, whatever the monomer was, so this in case it was ethene, you put poly in front. Easy enough. So the name is not based on the end result. The name is based on what was your starting component to actually create this polymer. Now, polyethylene is actually quite widely used as general plastics. So plastic containers, plastic, the insulation used on wiring. So if you've ever looked at, let's say, a chain link fence that has plastic coatings on the outside, a lot of plastics that are covering wires, right? So all wires have a plastic on the outside. Polyethylene has been used in many different applications, water bottles, Tupperware containers, all kinds. For sure, at some point today, you probably came across a polyethylene-based compound. Okay, so yes, and I've already mentioned this repeating unit. So let's look at another example. Okay, so here we have an example of, this is another common name for polyvinyl chloride. So just so you know, anytime you see the term vinyl, it can sometimes be referred to as like an ethyl. Anyways, we're only going to be looking at common, IUPAC names. So here we have our monomer is essentially chloroethene. We have an ethene group with a chlorine on it. So now we have a branch. Process is exactly the same. So again, they're showing 3 repeating units. They now are all single bonds, or you can show 1 monomer and ensure that you have the line on the outside of the brackets. So that's basically showing that this is the repeating unit. So the final result would simply be polychloroethylene, right? So this is an example of an addition polymer that's actually used quite a bit on, these are electrical wires that are a little bit of a thicker, like a tougher consistency. We now have coating on fabrics such as raincoats or upholstery on, let's say, on a couch or on a chair. So this type of polymer is now a little bit stronger in terms of its intermolecular forces. Because of this chlorine, we now have dipole-dipole. So even though the process is exactly the same, by having this branch on it, it changes the strength of the final polymer because we now have better, or I should say better, different intermolecular forces. Here's another example, polystyrene. So essentially styrene is, or this sty prefix can sometimes be associated with a benzene branch. So this is where we have, take a look at one of our monomers. Our monomer is basically phenylethyne. Or you can look at this as, I guess, no, that would be phenylethene. So the parent would be your double bond anyways. So here we have benzene as a branch. Same process. The monomers, those bonds are going to break. They now have all single bonds. So if we were to draw our condensed version here, it would look something like this. Here's my benzene with the line on the outside, right? So this would essentially be the IUPAC name would just be poly in front for the polymer. So this is actually, so polystyrene is also known as styrofoam. So styrofoam, if you take a look at it, is a very nonpolar. So you have large nonpolar benzene on an already nonpolar carbon-carbon base. So polystyrene is nonpolar. So this is what makes it sometimes ideal for food storage. Sorry, my dog's in the background making some noises, but it makes it ideal for food storage because most food is water-based. Right, so let's say you go and order a soup from, a takeout. You're ordering a soup in a takeout restaurant. So the soup sometimes will come in a polystyrene or a styrofoam container. And that's because soup is heavily based with water, and the styrofoam will not have it leak through because we know that polar and non-polar don't mix. So of course, this is amazing as like a food container. However, incredibly devastating when it comes to environmental impacts. So, you take your pluses with your minuses, but, obviously the environment right now is a hot topic issue. I don't think we see too many styrofoam containers. Maybe soup might be the only exception that you might still kind of see around. Okay, so I'm going to give you one that we'll draw together. But then I'll have you do one on your own. So we're going to show 3 repeating units with an addition polymer of 2-butene. Okay, so the method of drawing this is going to be important here. The double bond, so what we've looked at so far have only been like ethenes, right? Only 2 carbons. We now have something with 4 carbons in it. So when you are drawing it, you want to ensure that the double bonds are all connected or in the same line of sight as one another. Because remember, the bonds break along the double bond area. So that means even though I have butene, I'm going to basically draw this in a way so that the double bond is the only thing on this line. Okay, so you kind of just push everything out of the way is the easiest way to say that. So for example, if I were to do this, and, I can put the other one up here. So notice, let me use a different color to show you what I mean by that. This is 1, 2, 3, 4. This is still 2-butene, but I've drawn it in a way that I'm going to easily be able to see where the bonds are going to be broken and add up. So we're going to do the same thing for all of the others, of course, because it's 3 repeating units. So what happens here, maybe I'll do it down here. We're going to have, okay, so these are the double bonds that were originally up here. But we have to remember the other things that were on that molecule don't change. We still have the bute part of it. We still have the other carbon. So now it's just kind of like they're butanes, really, if you think of it. Right? So here's like one monomer, right? So here was one, here's the other, and here's the third.